Hello and good afternoon to all. Before starting this session, I'd like to express my sincere, heartfelt thanks to the host university, Karnataka State Akkamadevi Women's University, Vijayapura, Honorable Vice Chancellor, Professor Omkar Gowda Kakade, Chief Patron of this 5-day national level webinar on research and publication ethics. I also thank Professor R. Sunandamma, Registrar of the University and Patron of this webinar, and Professor P.G. Tatsat, Registrar Evaluation and Patron of this webinar, and he is also one of the favorite teachers, my guru and guide. Special thanks to organizing secretaries, Dr. Gavisiddappa Anandali, Associate Professor and Librarian in charge of the university. I also thank Dr. Shanta Devi T, Associate Professor, Chairperson of Department of Library and Information Science, Karnataka State Akkamadevi Women's University, for inviting me and providing an opportunity to present in this national level webinar. Seeking the blessings of all the elderly professionals, experts in the field, and all my loving teachers, I'd like to present a lecture on citation enhanced indexing abstracting databases. I have tried my best to provide credits, citations to the ideas and contents which I have used in this presentation. If there is any lacuna, it may be considered for modifications and correction at the later stage. So dear participants, let us start by unrolling the little history of this citation enhanced indexing abstracting databases. Let me start by asking a question to you. How many of you know or heard the name of Vannevar Bush and Eugene Garfield? Just try to recollect. Vannevar Bush and Eugene Garfield. I hope many of you are familiar with these popular names, particularly Eugene Garfield. Dear participants, in this presentation we are going to discuss or understand the history and the origin of content as enhanced indexing abstracting databases, meaning of citation, citation analysis, and citation resources. Then we'll be studying types of indexing databases, we'll try to learn the key features of the most popular citation indexing abstracting databases, namely Web of Science, Scopus, Google Scholar, ResearchGate. We'll be seeing the difference between the Web of Science and Scopus through various features, and also we'll try to see the difference between these paid commercial databases and some of free databases like Google Scholar. After that, we'll be learning some of the examples. We'll be looking into some of the examples of output by conducting a research in all of these databases. And lastly, we'll be providing you with some suggestions before concluding this session. Earlier, I have asked you regarding whenever Bush 60 years ago contemplated, among many other things, an information workstation, popularly known as the Memex. This Memex, a researcher would use it to annotate, organize, link, store, and retrieve microfilm documents. He is acknowledged today as the forefather of hypertext system, which in turn is the backbone of internet. He outlined his thoughts in an essay published in Atlantic Monthly titled "As We May Think." This article or essay is also famous by name Memex paper. Maybe because of a non-scientific outlook, the paper was hardly quoted and cited in scholarly and professional journals for 30 years from its publication. Jacoby in 2005 quoted Bush in comparing the similarity between whenever Bush and Eugene Garfield. The statement like this: our inaptitude in getting a record is largely caused by artificiality of the system of indexing. When data of any sort are placed in storage, they are filed alphabetically or numerically, and information is found when it is by tracing it down from subclasses to subclasses. That's what we do in index, right? It can be in one place unless a duplicate copy is used. One has to have rules to which path will locate it, and the rules are cumbersome. Having found one item, moreover, one has to emerge from the system and re-enter on a new path. Human mind does not work that way. It operates by associations. With one item in its grasp, it snaps instantly to the next that is suggested by the association of thoughts, in accordance with some intricate web of trails carried by the cell of the brain. Selection by association rather than by indexing may yet to be mechanized. Exactly at this point where Eugene Garfield enters. With his characteristic flavor for thinking and doing better, he envisioned 50 years ago in his landmark paper how the limitations of descriptor-based lookup for scholarly document in indexing abstracting publications could be overcome by using reference the references cited by the authors in the paper. This is a different approach than the one presented by the Bush, because cited references have always formed part of scholarly papers. They represent millions of past association in the form of highly structured, if not standard way. They can be reconstructed from source documents without the type of intellectual efforts implied by the Bush. Garfield got this idea for creating an index for highly successful shepherd from highly successful shepherd's citation, which traced, and still it is tracing, the court cases and decisions of each US jurisdiction. Garfield's unpublished master thesis for the MLS degree at Columbia University bore the title Shepherdizing the Scientific Literature. Frank Shepard was not the first, but was certainly the most famous for creating a citation index. As it was pointed out by Wimberg, the earliest Hebrew manuscript citation index dates back to 12th century. While Bush emphasized the associative thinking of individual researcher, Garfield built his idea on the constantly growing and already recorded collective associate thinking of invisible college of researchers through the network of references documented in their published papers. It is an important distinction. Garfield's vision was also right and much ahead of his time in recognizing how the legal citation index can be enhanced, adopted, and applied in scientific literature in order to produce a unified index without disciplinary boundaries, that is, subject boundaries. His idea of citation-based searching, resource discovery, and quantitative evaluation of publications serve as a basis for many of the most innovative and powerful online information services these days. By understanding this small history, how Eugene Garfield got this idea from Shepard Frank and Vannevar Bush, let us try to understand the meaning of citation. In order to define citation resources effectively, it is necessary to clarify what is meant by a citation and to highlight the importance of the citation and citation analysis in scholarly information. Citing is the process by which scholars give recognition to researchers by another academic researcher. A citation can be described as a written reference to a specific work or portion of the work, such as a book, article, dissertation, report, music composition by a particular author, editor, composer, etc. That clearly identifies the document in which the work is to be found. The frequency with which the work is cited is sometimes considered a measure of its importance in the literature of the subject field. Meaning of citation analysis. Citation analysis is therefore an attempt to measure the impact and the contribution of the research study in a specific field to the body of knowledge. Citation resources are tools used by the academics for keeping track of who are doing what research and the impact of this and their research within the discipline. What is a citation resource? A citation resource is also referred to as citation index, citation tool, source index, and subject index. Ritz in 2004 describes a citation index as a tool in which works cited during a specific year are listed alphabetically by name of the author cited, followed by the name of the citing authors, that is the sources. Full bibliography information for the citing author is given in a source index. In addition, a subject index usually lists articles by significant words in the title. Journal indexing helps to maintain the ethics and the quality in terms of the publication and increase the visibility, validity, availability, and readership of a paper. Journals can increase their research and impact by getting their publication indexed by one or more leading databases. Indexes are standards and certifications that journals manage to take if they compile with a set of principles and rules applicable to each useful indexing body. Simply put, or to put it simply, index is a standard system that different journals will be able to adopt if they adhere to the standards of the particular index. Types of indexing database. Traditionally, there are two types of indexing databases. Indexing and abstracting databases. Most of the indexing and abstracting databases started out as, and today also they remained as, a discipline-oriented reference sources, such as biological abstract, psychological abstracts, chemical abstracts, InSpec database, sociological abstracts, etc. While the second type of an indexing databases are what we are studying today, those are citation enhanced indexing abstracting databases. They are in fact indexing and abstracting databases, but they are enhanced with the citation aspects, citation counts, citation measures and metrics within them. And moreover, they are multidisciplinary. They are not stagnant to one particular discipline or subject. Their coverage is multidisciplinary in nature. These citation enhanced indexing abstracting databases kick-started by ISI Philadelphia in the year 1963 in the form of Science Citation Index. And this Science Citation Index remained unique resource for 40 years until Elsewhere launched its ambitious Scooper service in 2004. And then it was again followed by the launch of the Google Scholar beta version in the same year of 2004. If somebody wants to make a search, some of the synonyms for this citation enhanced indexing abstracting databases could be, or you can say the other terms for them is link-based citation references, citation scores for filtering and sorting results, software approach to citation searching, citation process. Web of Science, as I told you, was started in the year 1963, which is published in the past by ISI Philadelphia, later by Thomson Reuters. This Science Citation Index is now part of the Web of Science. Most important legacy of Eugene Garfield. He was the creator of this Web of Science Citation Index. Web of Science core collection, especially its 3 classical journal citation indexes, that is, Science Citation Index expanded as of now, Social Science Citation Index, Arts and Humanities Citation Index. Web of Science is officially launched in 1997. Earlier it was Science Citation Index. In 1997 it was renamed and launched as Web of Science, renamed as Web of Science Core Collection in 2014, with integration of all the 3 journal citation indexes, and it's expanded its coverage gradually from there on. The family of ISI citation indexes, which makes up the core of Web of Science, was created from get-go by the inclusion of all the references cited by papers in primary source documents. Web of Science covers all disciplines one can think or find in a curricula of universities in science, in the field of science, social science, arts and humanities. As I told you, there are 3 major database components in Web of Science, which all of them can be searched with single search strategy or single search mechanism. You don't have to search 3 indexes differently. Along with these 3 core journal citation indexes, it also covers through 2 chemical databases, namely Chemical Reactions Index and Index Chemicus, and also a Conference Proceeding Citation Index. These 6 indexes are part of Web of Science. The extended Science Citation Index is by far the largest component of Web of Science. There are several reasons for it. The most important is that Web of Science goes back the furthest to 1945 coverage. That means Web of Science covers the literature in science from 1945. While the coverage in Social Science Citation Index starts from 1956, that means after a period of 11 years, and in Arts and Humanities Citation Index from 1975. Thomson Reuters is a Canadian multinational media conglomerate that has a number of subsets, one of which is the Web of Science database. Web of Science was originally produced by Institute for Scientific Information, ISI, and is currently maintained by Cleverate Analytics. Web of Science journals recently added Emerging Source Citation Index. The articles that are indexed on these databases are popularly known as ISI articles. Web of Science has two types of journals, one with impact factor, that is JCR journals, and other without impact factor. These are called as ISI listed journals. You can check, you can go to the link provided below to make sure a magazine is indexed in Thomson Reuters Institute. ISI provides substantial factual information to know more about Web of Science through its ISI list of journals. Then it gives information about the essays by Eugene Garfield and the concept, and also it provides information of citation indexing, history of citation indexing on its website and blogs. Coming to the next database, that is Scoopers. Scoopers was launched in 2004 by Elsewhere. It was the powerful competitor of Web of Science and is attempting to challenge the dominating role of Web of Science. As of today, we can say by the statistics and the figures which is provided by both the databases, and many of the research works that have been carried out in comparison of Web of Science and Scoopers, that Scoopers has already taken the dominant position against the Web of Science. Elsewhere created Scoopers by extracting records from its traditional indexing abstracting databases such as GeoBase, BioBase, MBase, and enhanced them with citation references. Initially, Scoopers does not cover sources in arts and humanities, but has modest coverage to social sciences. Scoopers starts with coverage substantially in 1965. The breadth of coverage varies widely. The distribution of journals by major subject areas, as assigned by Elsewhere specialist, is reported on FAQ page of frequently asked question page of Scoopers. It clearly shows the focus of Scoopers in life and health sciences, chemistry, physics, engineering, and while periodically sources in social sciences of the journals. It covers patents from 5 patent offices, book series, conference proceedings, trade publications, articles in press, web pages, and other selected resources like institutional repositories, digital archives, special subject collections, as well as it covers the 100% coverage of Medellin database materials. Scoopers is the world's largest abstract and citation database of peer-reviewed research literature. It contains over 20,500 titles from more than 5,000 international publishers. In total, Scoopers has indexed 3,500 scientific journals. Scoopers is one of the Elsewhere's product, and using its information requires subscription and payment. It is not free based, it is a payment based subscription access you can get. You can refer to this link provided below to make sure a journal is indexed in Scoopers. Like Web of Science, Elsewhere also provides substantial factual information and else files about this to know about the Scoopers, which act as an information hub for the seekers or researchers to know about the Scoopers. You can look for the list of journals, list of publishers, list of open access journals covered by Scoopers on its website, and blogs. Let us try to differentiate between this Web of Science versus Scopus with certain features. Who is the publisher of Web of Science and Scopus? As of now, Clever8 Analytics, formerly Thomson Reuters Institute of Scientific Information, was the publisher of Web of Science. For Scopus, it is Elsewhere Publications. Number of journals covered by Web of Science is greater than 13,000. Number of journals covered by Scopus is greater than 20,000. Content-wise, Web of Science covers natural science, biomedical sciences, engineering, social sciences, arts and humanities, strongest coverage of natural science and engineering. While Scopus concentrates more on biomedical sciences, natural science, engineering, social science, arts and humanities, strongest coverage of biomedical and natural sciences and engineering. Database covered: Science Citation Index, Social Science Citation Index, Arts and Humanities Citation Index, then the two chemical databases, and Conference Proceedings Citation Index. For Elsewhere, 100% of Medline database and MBase Plus and other contents. Time period covered: Science components 1990s, Social Science components 1975, Arts and Humanities components 1975 for Web of Science. Scopus initially covered 1996 to present, now includes substantial content prior to 1996 with some back to 1823. Updating frequency: Web of Science is updated weekly, Scopus is updated daily. Citation analysis: Web of Science, yes, includes citation tracking, citation count, and author H-index calculations. For Scopus, it is one and the same. It also covers citation tracking, citation count, and author and H-index calculations. Controlled vocabulary? No. Web of Science don't have any controlled vocabulary. Scopus, it also does not have any controlled vocabulary, but Scopus specific controlled vocabulary is adopted to some extent. Keyword field index includes indexing terms from references taken from other databases such as PubMed and MBase. Export features of references are allowed in both the databases. You can export the references of the citations from these databases. Alert features: you can set an alert and you will receive as and when there is an update in the subject that you are interested, or the person you are interested in knowing the citation updates or new citations received on particular journal, author, or subject. Relative strength: more through coverage of older literature for Web of Science. Ability to analyze search results by author, affiliation, country, journal, book, title, and broad subject categories of Web of Science. Web of Science can sort search results according to how frequently the articles have been cited. In case of Scopus relative strength, the database is more versatile, got more versatile search and refine options, including the ability to search for first author. Tools for analyzing search results by author affiliation, country, journal title, and broad subject categories are also included. Scopus author identifiers are broadly assigned, useful for distinguishing among publications from authors with similar names. Growing book chapter coverage, especially for social science and arts and humanities. In Scopus, one can search using controlled vocabulary terms, but they are confined to the Scopus Embase database vocabulary. Comparison between Web of Science, Scopus, and Google Scholar. Three databases present different approach to citation search services. Web of Science and Scopus are commercial databases at the expensive end of the spectrum for good reasons. Google Scholar is currently an open access database, still in beta version after its launch in November 2004. The expectations are different for fee-based and free-based databases. But open access should not provide excuse for ill-convinced and poorly implemented search options and the potential misleading presentation of the information. According to Garfield, when Web of Science was established, a manual method was adopted to assign the journals to categories. And after this, the so-called Hein-Colson algorithm was used to assign new journals. This algorithm is based on the combination of cited and citing data, but it has never been published. Besides this, Cutts and Hicks and Ruffles have indicated that Web of Science classification system is based on the comprehensive consideration of citation patterns, titles of journals, and expert opinion. In case of Scopus, there seems to be no information at all on the construction of its classification system. Scopus, though, follows all science journal classification of two levels. All of them can give the impact factor for many journals and the H individual index for many researchers, but each of them has a limitation either of representative or of excess, which need a few explanations to ensure the better use of them, depending on the context one wants to use the results. Here are some examples to compare the search with different tools. Building a multi-million record database incurs multi-million-dollar investment just to subscribe to the journals, administer their processing, and record their standard bibliographical data, abstract and descriptors. For about 1 million papers per year in the most recent period, adding 20 to 22 million cited reference per year increases those traditional costs enormously. So you cannot compare Web of Science and Scopus with the Google Scholar. Web of Science and Scopus offer very powerful features for browsing, searching, sorting, and saving functions. Google offers limited and sometimes dysfunctional search options for well-structured data. Bibliometric search to explore the size, source base, breadth, and composition of a data, or the literary genealogy of a specific subject are exceptionally well facilitated in Scopus and Web of Science, and are practically non-existent in Google Scholar. The content of the data are updated regularly in Web of Science and Scopus. In Google Scholar, the updation is instant as of now. Earlier, it was maybe a 6 months or 3 months dormant period was observed by this Google Scholar. Scopus have abstracts, which is a good ratio. and slightly better than the ratio in the Web of Science. Simply because Elsewhere has been adding abstract for articles in its role as an indexing and abstracting service provider. While ISI clear policy is that it does not create abstract but just use if it is available in the article itself. In addition, Web of Science makes it also clear that it started to add abstract to Science Citation Index from 1971 and to Social Science Citation Index a year later. Google Scholar best searched with Herzing's Publish or Perish launched in the year 2004. Google Scholar has some disadvantages. The low data quality found in Google Scholar raises question about its stability for research evaluation. Google Scholar is a free service, and for many who consider it to be a gift for the world, it may be a anathema to say any but good words of it. It is also to be emphasized that it is a joint gift by some publishers and or their digital facilitators, the content part, and the Google, the software and the service operation part. Also, number of productions not easily visible on the web as posters, presentations to conferences, master's and PhD theses and other academic reports, technical reports, is hard to find in Google Scholar. Google Scholar does not offer publishers list, journal list, neither any clue about the time span or the disciplinary distribution of records. Its search softwares prevents the users from finding any reliable data about their traits of the databases. Compare this to the similar free professional sites of Highware Press, which hosts the full text of nearly 2.5 million scholarly articles from high-impact journals, including 9 lakh open access articles. It provides not only well-structured and informative data, but its publisher partners, journals, and archive composition, but also offers a sophisticated, still easy-to-use search and navigation software tailor-made for the exquisite archive. GS, that is Google Scholar, lack of competency and understanding of basics issue of citation indexing. Google Scholar fails even in implementing the most basic Boolean or operations correctly, as per Jacobs. Google Scholar's native interface is not very suitable for bibliometric analysis. Publish or Perish is used primarily in conjunction with Google Scholar, but also offers extensive data import facilities, providing the ability to import amongst others. Publish or Perish automatically calculates a wide range of metrics. Google provides minimal information about the content of Google Scholars. Its list of frequently asked questions provides some information about the source features. If you want to download the Publish or Perish, please refer to the link given below. Coming to the ResearchGate, it is considered to be the second richer indexation site. It is based on the individual registration to the database, and those people do not register might be low or not visible in ResearchGate. If their potential co-authors have not registered their work either, for this, the ResearchGate is interesting when available, but its metrics are not comparable from one individual to the other. ResearchGate seems to be, for now, the best communication tool between the researchers to communicate their results and exchange results, ideas, projects, etc. It is much more than an indexation and bibliographic site. It is a tool that helps the research management and prospective and accelerates the diffusion of results to the wider audience concerned by the specialized topics. The ResearchGate will present all the production that a researcher will have loaded itself and its co-authors. Thus, there is a virtually no limit and absolutely all the productions can be loaded, even databases, articles, books, chapters, code, conference papers, cover page, data, experiment findings, methods, negative results, patents, posters, presentations, project, questions, raw data, research proposal, technical reports, theses, working papers, etc. can be posted or loaded on ResearchGate database. Through this citation enhanced indexing databases, one can understand or calculate different types of metrics. Let us try to understand some of the basic metrics that these databases provide. Publications, total number of publications per academic. Citations, total number of citations per academic. H-index, an academic with an index of H as published, H papers, each for which has been cited in other papers at least H times. HIA norm, academic age, where HIA norm normalizes the number of citations for each paper by dividing the number of citations by the number of authors for that paper and then calculate the H-index of the normalized citation count. Academic age, number of years lapsed since the first publication. Impact factor, Thomson Scientific defines the annual journal citation report, JCR, impact factor as a ratio between the citation and the recent citable items published. Thus, the impact factor of the journal is calculated by dividing the number of current year's citations to the source items published in the journal during the previous 2 years. Hits, number of hits a particular document is receiving on the, particularly for Google Scholar. Number of hits or counts is also a even greater measure because it would include blogs, general websites, and many more syllabi. Conference papers, newsletters might be counting of hits on internet search engines such as Google's. Mentor index, an index that measures the mentoring impact by the research impact or the performance of the students produced. Citation relations between the journals, notions of the relatedness of the journal and the category of the subject. Having discussed the various features and having compared these citation enhanced indexing databases, now let us try to understand the problems and challenges of these citation databases. Critics note that these popular citation enhanced indexing abstracting databases cover mainly the English language journal articles published in United States, United Kingdom, and Canada. They also note that databases are limited to citations from journals and papers indexed in ISI database. Databases provide different coverage between different fields. They do not count citations from books other non-ISI sources and have citing errors, examples, homonyms, synonyms, and inconsistency in the use of initials and in the spelling of non-English names, as noted by Lawson. Overall, journals published in the countries like US, UK, Netherlands, France, Germany, Switzerland represent a larger portion of journals indexed in Web of Science and Scopus than they do in Ulrich list of journals. Larvey has shown that more than 50% of the all articles indexed in Web of Science are published in journals owned by those 5 commercial publishers. There is an issue of defining the geographical origin, whether the geographical origin has to be identified by the place of the journal or the publisher's place of journal or the editor place of the journal. For detailed summary of the potentials of pitfall and citation analysis for the assessment, please see Wallen 2005 article. Suggestions and conclusions. These citation enhanced indexing abstracting databases should be used with caution, especially when comparing different fields, institutions, countries, or languages. The bibliometric community should continue its efforts to develop methods and indicators that include scientific output that are not covered in Web of Science or Scopus, such as field-specific and national citation indexes. As a conclusion, there is no definite criteria for ranking these indexing bodies. All of them have some advantages over the other. ISI, due to its much longer history and being the only information provider, is still more popular worldwide. However, the scientific progress of some countries is measured by the number of papers published in Scopus. It is also worth noting that the journals with high scientific credibility are usually indexed by both Scopus and Web of Science. In general, according to Annie Will Herzing in her book Publish or Perish, Scopus provides a higher citation count than ISI, both in science and in social science and humanities. Scopus appears to have much broader journal coverage for the social science and humanities than ISI and hence provides a fairer comparison. However, in ISI academics working in the science has an average of 17.5 times as many citations as the academics working in the social science and humanities. In Scopus, the difference is reduced to 7.5 times. However, for the time being, Scopus is hindered by its lack of coverage before 1996 documents. This means that for the most established academics in the science, Scopus will lead to lower lifetime citation counts than ISI. In social sciences and humanities, a substantially increased citation count is likely for the academics who have published the majority of their highly cited work after 1996. The big difference between the database is the content. In Scopus and Web of Science, editors select and curate which journal, book, conference proceedings, and other materials are interested. Google Scholars, on the other hand, will include everything that is found via automated process crawling, which means that there is no quality control or filtering. Consequently, Google Scholar has much more content, but it is less structured and it is more likely to include errors in the metadata as well as including documents like presentation, posters, grey literatures, websites, and others. Scopus and Web of Science prioritize English literature, while Google Scholar is more inclusive to different languages. All three databases, though, while a lot of content is present in all, differ subsequently in coverage, and therefore it can be useful to consult all of them while doing research. Thank you, one and all. I sincerely thank the Karnataka State Akamadevi Women's University for providing this opportunity to me to present my lecture in this national level webinar. Thank you, one and all. If you have any doubts, kindly contact me. I will be available through my mail and phone numbers provided in this